This video is going to look at two important types of graph that we might see when studying kinetics of chemical reactions. The first type will be time versus concentration graphs, and the second type will be concentration versus rate graphs. Let's start with an example of a rate expression that has come from experimental data. And you'll notice in this rate expression that the concentration of X is given to the power of 0, meaning that the order of reaction with respect to the concentration of X is 0. This means that the concentration of X does not affect the rate of reaction. So even as my reactant X is being used up, the rate will not change. So let's first consider what a time versus concentration graph might look like for this reactant. In these graphs, we're going to have time on the x-axis and concentration on the y-axis. Before we consider the shape of this graph, we need to remember that to calculate the rate or identify the rate on these graphs, we need to consider the gradient of the line. And we've just identified that if the order of reaction is 0 with respect to X, then the gradient of the line is going to be consistent throughout this reaction. We also know that because X is a reactant, its concentration is going to decrease throughout the reaction, so we would expect to see a straight line decreasing something like this. Here we can see clearly that the concentration is decreasing as reactant X is used up, and because it is 0 order, the gradient of the line must stay the same, which is why it is a straight line and not a curve. In order to consider what a concentration versus rate graph will look like, let's take 3 points on the y-axis here and call them A, B and C. And let's now plot those on a concentration versus rate graph. This time the concentration will be on the x-axis. So if I was to calculate the rate by calculating the gradient at points A, B and C on the red line on my left-hand graph, as we've discussed, the rate is identical at all 3 places, meaning that the line on my right-hand graph is actually just going to be a flat, straight line, something like this. And this shows that it doesn't matter what I do to the concentration of X, the rate is always staying the same because the order of reaction is 0 with respect to X. Let's now consider a different rate expression. In this rate expression, I can see that rate is proportional to the concentration of Y to the power of 1. This means that the order of reaction with respect to the concentration of Y is first order. So what does first order mean? Well, it means that rate is directly proportional to the change in concentration of Y. So if the concentration of Y increases, rate will increase, and if the concentration of Y decreases, the rate will decrease. Let's consider then what a time versus concentration graph might look like. As with the first example, we know that the concentration of Y is going to decrease because it is a reactant in my reaction. But in this case, because it is first order, as the concentration of Y decreases, the rate is also going to decrease. So how will that look on a graph? Well, if the rate is decreasing, then the gradient of my line must also be decreasing. So we end up with a curve that looks something like this. Let's double check that the gradient of my line is decreasing by choosing 3 points in the reaction, A, B and C, on the y-axis, and make sure that a tangent to the line at that point is getting shallower and shallower. As you can see, the tangent, as I move through my reaction, is becoming shallower, meaning the rate is decreasing as the concentration of Y is decreasing. So let's now try and plot that on a concentration versus rate graph. From the left-hand graph, I can see that the rate at point A is the lowest, followed by B, followed by C. So my line of best fit in this case looks like it's going to be a straight line, this time showing a proportional increase as the concentration of Y goes up. And given that we know that rate is proportional to the concentration of y, this is exactly what I would expect to see. Let's now have a look at a third rate expression. In this rate expression, I can see that rate is proportional to the concentration of z squared, meaning that the order of reaction with respect to the concentration of z is 2. This means that when I change the concentration of z, I see an even greater impact on the rate compared to a first order reactant. So, what might a time concentration graph look like in this case? Well, again, I know because Z is a reactant that the concentration is going to go down. And because I know that rate is proportional to Z squared, I might expect to see an exaggerated version of the first order graph that we saw beforehand. The concentration of Z will drop more quickly at the beginning, but then flatten out more quickly as the concentration changes. As with the first order graph, this actually is a very similar shape, so make sure in exam questions you just clearly show that it decreases quickly at the beginning, but then curves until it plateaus. Let's double check that the rate is slowing down rapidly by considering points A, B and C again. And let's now consider what a concentration versus rate graph might look like for this second order reactant. Well, because I know that the order of reaction with respect to Z is 2 in this case, every time I increase the concentration of Z, my rate is going to go up by a disproportionate amount. And we can see here that the increase in rate between point A and B is much smaller than that between B and C. If I were to add a line of best fit, it might look something like this. And here you can clearly see the exponential increase in the rate as I increase the concentration of Z. Let's now try and summarize the key points from this video. So for a reactant that is first order, in fact no, let's start with 0 order, the time concentration graph would show a straight line decreasing. And because the concentration of a 0 order reactant does not affect the rate, we would see a flat straight line on the concentration rate graph. For a first order reactant, we would see a smooth curve that drops at the beginning and then flattens out over time. And because the concentration of a first order reactant is proportional to the rate, we would see a positive linear correlation on the right hand graph. Finally, for a second order reactant, we would see a similar shape to a first order reactant on the first graph, but might expect it to decrease more rapidly at the beginning and shallow out more quickly as the concentration changes. In reality, first order and second order reactants look so similar on that first graph that we would need to convert the data by calculating the rate and then plotting a second graph with concentration and rate to actually identify the difference. Because the second order reactant on the right hand graph shows an exponential increase. And this is because the rate of reaction is proportional to the concentration squared, which is why we see that steeply increasing line. I would recommend, if you get this kind of question in an exam, that you try and think your way through them instead of memorizing them. Hopefully this video has been of some help.